Oké. Nou, welkom iedereen in de nu wat bredere groep. So welcome everyone. I'll start in English because our first speaker, Michael from Fraunhofer, does not speak Dutch. And he will have his presentation in English. So welcome everyone. I've just started the recording. So be aware that what you say will be recorded, and we will also put the recording online afterwards for other people to learn about this webinar as well. So a brief introduction on our program. So we start with the webinar first with an explanation by Michael on the SensorThings API standard itself. And then he'll go into an introduction of the Fraunhofer implementation of the SensorThings API. Then Geonovum will give an introduction into their implementation of SensorThings. And we will finish up this webinar with an introduction into a number of data sets on groundwater levels by Philip Nienhuis from Waternet. So that's our program. And then in the afternoon we will start hacking. And we have today for hacking, tomorrow, and then Thursday morning we'll do a wrap-up of the results. And in Thursday afternoon there's a seminar organized by Logius where we'll give a short presentation on the most important results we achieved to a broader audience. So that's our program, and I think I'll quickly move on to the content. So I'll do these things. I think I'm going to mute all others. If you have any questions, please ask them through the chat. So, Michael, the floor is yours. If you want to use the mouse to advance the slides.
Thank you very much. So, my name is Michael Jacobi from Fraunhofer ISB, and I will have a two-part presentation. The first part will be about the OGC SensorThings API, so the standard itself, and the second part will be about about our Fraunhofer open source implementation of that standard, which is called Frost Servers. Okay, so probably many of you know the OGC. The OGC is the Open Geospatial Consortium. It's a big consortium of over 500 companies and government agencies and universities and so on. And their main objective is to geo-enable the mainstream IT, and they try to achieve this by developing publicly available standards like you may have heard of CDGML, WaterML, and so on. So how does, you may ask, how does OGC and IoT fit together? So IoT deals with sensors and actuators, and the sensors and actuators actually have a location and they interact with the real world. So geolocation is actually inherent. And there's a project or a set of standards that was developed by the OGC, which is called Sensor Web Enablement. The objective is to enable developers to make all types of sensors accessible and usable via the web. And this started in the 1990s by NASA, and since 2001, it's the work is done by in the context of OGC, and many meaningful and standards were created. You probably heard of them. For example, the Sensor Observation Service or the Sensor Blending Service or Observation Measurements. And the standards do not only deal with sensor data, but also, which is probably even more important, with the sensor metadata. Because without knowing what and where and when I sensed, the data is not very helpful. Okay, so the old SWI standards have some, I would say, drawbacks. They are using quite verbose XML encoding. They use SOAP bindings, and they're quite complex to use. For example, they do not allow browsing or pagination or publish subscribe. So the idea of SensorThings API was to take the core functionality of these standards, which are well known and used and have proven successful, and to lift them to the current level of technical, to the current technical level, like web technologies and so on. So the OGC SensorThings API is a standard for exchanging sensor data and metadata. And it works, of course, for historic data and for current or for live data. It is encoded, the data is encoded using JSON, and the API is based on the RESTful principles, so it's HTTP based. And it's adapting some URL patterns and query options from OData, as we heard before. And it also supports publish subscribe via the MQTT protocol. So putting this all together, it's easy to understand and to use, and you can actually discover the content of a whole server just using your web browser, if you like to. The standard itself is divided. It's not one standard actually, but it's multiple standards. So there are currently two parts. The first part is called sensing. It deals with everything related to the sensing domain, and it was published in mid-2016. The second part is called task and core, which is dealing with actuators, and was published at the beginning of this year. And the third part that is envisioned but not yet published is called rule engine, where the idea is to bring the sensing and the actuation part together and to define rules how actuators should or when they should act based on the sensor inputs. In my presentation, I will only focus on part one, the sensing part, because this is the most prominent one. So this part one of the SensorThings API standard is itself subdivided in one mandatory part, which is basic read and write, basic read access. So everyone that calls themselves compliant to the standard has at least to fulfill this requirement. And the other requirements, so the majority of the standard is optional to implement for a server. So they are called extensions, and there are a lot of them, like filtering, create, update, delete, batch processing, and so on. As you can see, there are also two extensions for the MQTT protocol. One where you can create observations, and another one where you can subscribe on changes on new entities. Last but not least, the standard also defines some type of conformance test. So there actually is a conformance test and a validation process. You can get your implementation checked and validated officially that it's compliant with the standard. And it also tests which of the extensions you support. So how does the standard work, and what's actually the content of the standard? I want to divide this again into two parts. First of all, I want to present the data model, and then I will show the API, how to manipulate that data model. So the data model itself is not that big. So we see the different types of entities that exist in the data model. It's like a UML class diagram. And the bottom left, you can, let's start there with thing. So you see the class thing has different properties, one called name, one called description, and another one called properties. This is some special kind of property because you can put anything in there you like. It's quite useful. We will come back to this later on. And then you have relations between the different kind of entities. So a thing can have locations. Actually, a thing can, of course, only have one location at a time. But this here, the multiple relation indicates that you can have different representations of the same location. So you can have one representation as GPS coordinates, you can have one in city GML, and so on. And things, of course, have historical locations. They can move over the time. So, yeah. On the top left, there's the other important class that comes from the name SensorThings API, the sensor. It also has, of course, name, description, and some metadata that can again be in basically any format, and you have to put in the encoding type what is the encoding of the content of this metadata property. So in the middle, there's like one class that brings together all the other ones, which is called data stream, and it's more of a virtual concept. It's not something you can easily grasp, but it's a concept to structure the data. So data stream links exactly one sensor and one thing, and it more or less means that the sensor is attached to that thing. Then together with the sensor and the thing, you have an observed property. So that's a property of the real world. What is observed, like it's the temperature or humidity or so on. And then you have a bunch of actual observations. So with the timestamp and a value, where you can have your actual readings of your sensor. Now, each of these observations can have a feature of interest. So feature of interest and thing are two things. There's a lot of confusion and a lot of questions all the time, how they relate. Because there are different types of sensing. There's like the standard sensing, I would say, which is in situ, like you have a sensor here and it's sensing actually right here, like a temperature sensor or something like this, or heart rate sensor. But you also can have remote sensing, for example, webcam or camera that is located here and observes over there, or a satellite. There's even more distance between that. So for in situ sensors, the feature of interest and the location of the thing are the same. The feature of interest is actually what is observed, and the location of the thing is from where am I observing. Okay. So the data stream has some additional properties like the unit of measurement. What unit am I measuring in, like kilogram or centimeter or degrees Celsius? And it also has property observed area, which is, I think, probably most of the time it should be auto-generated by the server. It's actually some convex hull of all the locations of all the feature of interest of the observations. So if I have a data stream containing 3 observations, like here, here, and here, then the observed area is like the triangle defined by those points. So we can easily query or see from the data stream, okay, it has observations in this area. And the same goes for the phenomenon time, which is basically the start and the end of all the observations to that data stream. Okay, so now we've seen the data model. The question is, how do we actually store data, create data, search for data related to that data model? And these are the basic operations via HTTP. So we have a base URL on top, which can be arbitrary. So the first part, the first mandatory part is the version number. So the URL always has to contain the version number, and from now on in the following, I will start with the version number for the URL and leave the rest out. So you can read, there's one special operation, you can get the index, so-called index. It's basically a list of all the classes that exist in the standard. The more interesting parts are, you can read all the entities of one type. So a collection, for example, all the things, if you type /things, then you get a list of all the things. Or you can access a single entity by ID, which was not shown in the previous slide. So every entity has, of course, an ID. It was not explicitly shown in the class diagram. So basically, whoever worked with the HTTP and REST commands, this is straightforward. More or less, you can create an entity by posting to the collection. You can update an entity by using HTTP patch, or you can replace an existing entity by HTTP put, or you can delete an entity. I will show some examples and the actual result you get when calling, when doing these commands. So if I do HTTP get on /things, I want to get all the things. I get back like a JSON object with a property called value, and in that there's an array, and this array is just a representation of things. So we have the name, the description, we have some properties. What is probably not so straightforward is this part here below. So only the basic properties are included directly in the JSON. The links to other entities are just included as links. So we just have for locations and for the data streams and so on, we just have a link. If we follow that link, we get, of course, again, a list of that entity. And we have the ID and additionally a self link. Okay, if I add the ID in brackets in the URL, so things 1, I only get, of course, one thing. I can get related entities. So these navigation links we saw before, I can follow them, for example, by putting things 1/data streams in the URL. And then I get only the data streams related to that one thing. This can also be chained. If I want from this data stream, maybe the observed property, I can add /observed property to the URL and so on. There are features like pagination. You can add query options to the URL. For example, so all the commands, I would say, in the SensorThings API start with a $sign. And the question mark here is URL syntax to separate the address from the query parameters. So we have a command which is called top, and you can say, okay, it has a value 4. I just want the first 4 entries, and I also want to get the count. And the result is I get an additional property, which is the count. It says, okay, in total there are 16 entries, but as I only want to view 4 of them, I get a next link because there are more. And the next link, if I click or follow the next link, I will get the next set of results. Of course, you can do sorting. The command for that is called order by. You can say ascending, descending. And you can also use functions on properties. So you can order by, for example, the length of a property. And you can do filtering. For example, filter observations with a result greater than 5. There are a lot of functions you can use in filtering and ordering. like basic comparison operators, greater than, greater, equal, equal, less than, not equal, logical operators, mathematical operators, string functions, and so on. More important, I would say, are the geospatial functions on the left. So you can also filter by, for example, distance to a point. You can order by distance to a point. And you also have date times and functions, and time functions you can use.
There's a question in the chat.
Okay, yeah, can the URLs have spaces? They can have spaces, but the browser, also, you have to actually encode them. So if I'm not mistaken, a space will be percentage 20 after encoding.
Yeah, so you need to use URL encoding.
Yes. Yes. Okay, so a few examples for filtering. You can filter all observations with an even result by saying, okay, result modular 2 equals 0. More interesting, you can get, for example, the observations of the last hour by filtering the phenomenon time, which should be greater now minus the duration of 1 hour. And you can also use not only the basic properties of the entity, but related, you can follow navigation links here. So I'm filtering data streams, and I'm filtering them on the property name of a related observed property. And of course, you can combine all those stuff together and make quite complex queries. Then there are further options. For example, the select keyword you can use to reduce the payload you get in return. Then you don't get the whole object, but only the properties you select. And one of the most important commands from my perspective is the expand command. So the navigation links are just links, but you can actually use expand to tell the server fetch the data that is behind that link and inline it in the document. So you don't have to do additional calls, but you can tell the server to actually get it for you. So normally I would get, without using expand data streams, I would get only the link of the data streams, or one link to the data streams collection. But if I use expand, I get the actual data streams inlined again. And you can also, of course, combine them and nest them. Also, you can have different levels of nested expands and select, and also filter, and all the query parameters. So the query language is quite powerful, and that most of that is because it comes actually from the OData standard. So the query language is not something that was invented with SensorThings, but has been standardized by the OASIS for many years. Okay, so that is the first part about SensorThings API, and the second part would be about, or will be about, our open source implementations. So are there any questions regarding the standard yet?
I'm not sure if it's useful for this particular thing, but as I understand, there's a relational database behind the implementation normally, yes?
Well, the standard itself does not enforce anything. It just defines the data model and the API. How you implement it is totally up to you. If you use a triple store or a time series database or object store or relational database, that's at least not part of the standard. Our implementation uses a relational database, but also provides an interface where you can implement or your own data adapter, I would say. And you could also use a triple store or object store, time series database, or whatever.
Yeah, my question is because like you said, the filtering language is quite powerful, so you can do a lot of filtering.
Yeah.
It also means, for instance, for a relational database, you need a lot of indexes and ultimately performance where you have a lot of data.
Yeah.
Michael, can you quickly repeat the question because
sorry,
to the microphone? Yeah.
Okay, so the question was about using relational databases. So
the question really is how do you make it performant using this powerful querying, filtering, so to speak, on a relational database when you have a lot of data.
Okay, so to repeat the question for the webinar, the question was, if you have that kind of complex query language, how do you make it performant with a relational database? And for our implementation, at least I can say for the Frost server, that we are delegating as much as possible to the database, and of course we heavily use indices for that. But so far we have. I'm not 100% sure on the latest data, but we have deployment with, I think, over 100 million observations. And yeah, of course, query times go down to some degree. If you don't scale up the hardware, the performance will go down. And there are, of course, you can think of quite complex queries that will actually take some time. For now we have still scenarios using those databases, and the performance works for them. Sometimes we keep adding new indices for that.
Another question.
Yeah.
Is there a way to gracefully indicate that you are not complying to the full standard? So that, for instance, there are wonderful kinds of query languages, but maybe you just want to only do the observations. And is there a way to indicate to a user that is expecting the API that it will say, well, listen, this part of the API I'm not doing for you. So you have to make sense. And maybe over time you will expand.
Okay, so
part of the standard.
So to repeat the question, it was, is there an option in the standard to say you're not fully compliant to the standard, but compliant to some parts? And if a user can detect that you're only compliant to a specific part of the standard. Regarding the mentioned extensions, so first of all, in version 1.0, there's no possibility to detect this, but it is tested in the validation process. So you will get a result which says, okay, you comply to this and that you are not compliant to, but there is no way to access this information in a machine readable way. But in version 1.1, which is close to be finished, there is additional information available, exactly what kinds of extensions you support in a machine readable way.
Is there a way maybe to document that? Because any specific API, I guess you would provide it also with an API specification, for example, in OS format. So is there any way to document it there, that you say in the OS file, well, this is the API and it complies with these parts of the standard, for example?
I'm not 100% sure if I get that question.
Okay.
You mean by API specification something like Swagger? Or
yeah, it's Swagger. Yeah,
okay.
Yeah, it's Swagger. Yeah.
Okay, so the question was if there is any kind of API documentation like Swagger or something similar, and maybe this could be a place to highlight that you're not fully compliant.
Exactly. Yeah.
we tried actually doing a Swagger documentation for the API, but the API is so powerful and generic that and also recursive, which is not possible to express actually with Swagger. So
okay.
I'm not aware of any tool that also can cover this level of complexity of a query language.
Okay.
Related to the last two questions, there's lots of activity in OGC right now to have a, let's say, common approach to APIs. It's all based on open API and also with the common part, which for instance says on the API that you have a /conformance REST call, then you can see is there, maybe it's a difficult question, it's more a question for OGC, is there any plans to align the SensorThings API with that activity? So I realize that it's based on OData Oasis currently, SensorThings API, but in practice also is quite a hassle to implement and to align that with the current work, because everything is now redefined, WFS, WCS, all based on open API.
Okay.
It's hard to repeat it.
Yeah, I'll try to recap that question. So the question is, a lot of OGC standards are now being adapted to have a unified model, more or less, or unified appearance.
Yeah, they're starting from scratch, basically.
Yeah, okay. So, and that is a bit different than how SensorThings does this. So the question is if they're planning to align to that general OGC approach. To be honest, I don't know. I guess, yeah, I mean, it probably would mean a lot of changes to the SensorThings API. So I guess it will not happen that quickly if it happens.
Maybe I can also answer part of that. I'm a member of the OGC architecture board, so I'm well aware of the things that just mentioned about OGC moving towards RESTful APIs and Swagger or open API specification playing a prominent role. At this time, there is no effort at all to harmonize this with SensorThings API. I don't think it's even on the radar at the moment. And I can also understand why it's difficult. As Michael mentioned, APIs based on OData, you can never fully cover using open API specification. So the best you can do is give an open API specification document that gives you a short introduction that helps you on your way, but it can never fully express everything the SensorThings API can do. So the short answer is no, there's currently no effort going on. Should there be? Well, maybe, but it will be difficult.
Okay. So I think there's one last question over the chat, and then I'll have to continue because of time issues. So the question is, how do you ensure that everybody defines temperature in the same way over different SensorThings servers? So that is a question regarding semantic interoperability that is actually not part of the standard definition itself. So this is open. Yeah, you can, of course, arrange and say, okay, we're using a defined vocabulary like for air qualities from the EU, for air pollution, and we're referring to that. Or you can define your own terms. I think, yeah, that is a good decision because this is a more technical standard and the other one is more an organizational question. How do we call our things or observe properties or units and so on? So this is not covered actually by the standard itself. You're free to use any definition that you like. Okay. So the second part is the Frost server. It's actually short for Fraunhofer Open Source SensorThings API server. So Frost is better. It's published as open source, LGPL license, and it's actually the first implementation to include all the extensions. So the whole standard document is supported. It is based on Java EE, Postgres database, and PostGIS. But as I said before, all database access is abstracted by an interface, so you can actually do a different implementation of that interface, and you can use a different data store behind. But of course, you have to implement all the functions that we saw. So also all the geospatial functions, which is not that trivial. In our implementation, we're giving that basically to the database in PostGIS. Okay, it's actually the official OGC reference implementation right now, and what I like most about it is the scalability. So we run it on different size of hardware. We run it on Raspberry Pi. I do that at home. And we run it on our development machines. We run it in local clusters, and we also run it in data centers. So quite scalable. Agenda is quite short for that one. We have a bit of the history, then a few features that go beyond the standard, how to deploy a server, and then a quick look at the Frost landscape. So in the beginning of 2016, we started the development even before the standard was released. And end of 2016, we had officially released our first version, including the create, read, update, delete, data array, and MQTT. We added additional features. Basically, the only missing one was then, after some time, batch processing, which I guess nobody has ever used here, but it's implemented. We also added Docker support. After we fully implemented the standard, we worked on horizontal scalability, and we added Helm charts for deployment in Kubernetes. And in mid of this year, we added tasking because the tasking standard was just released at January this year. Okay, so some features that are quite helpful that go a bit beyond the standard or maybe are not so clearly defined in the standard. Observations has a result with the type of any, but what can any be? Of course, it has to be encoded in JSON, so it has to be valid JSON. The features of Frost Server are new now that it's truly type conserving. So if you put in a double value, you get back actually double value. So that I've seen server implementations that cast everything to string, and it's legal actually defining this or looking at the standard. So you're compliant to the standard, but it's to my feeling not very helpful. So if you put in a number with the exponential, like in the example here, then you actually get back exactly the same format with the same precision and so on. You can also use this information for type-specific ordering. So yeah, the implementation I mentioned that casts everything to string. Of course, if you want to order numbers and you have them only as string, then you have a kind of a strange ordering sometimes. And we also apply the type safe filtering on them. Okay. Then the next point is we've seen before that the thing has a property which is called properties, where you can put in any JSON objects or any additional information that you want. And we propose to make this standard for all the entities because we experienced that it's very helpful in practice to store information related to other systems and external systems. And this is something that actually was accepted by the standardization group and will be part of the version 1.1 of Sensing, which is, I guess, will be released at the beginning of next year. So it's close to be finished. As you can have like complex JSON objects within these properties, we allow also filtering on sub-properties of this JSON objects. So you can have a path that goes inside the JSON object, which is very useful for stuff like you can add semantics. You can say, okay, this thing is actually a room because I have a property. I add the property type with room. And of course, here you see the type say filtering. We can filter by string, by integers, or we can also filter by Boolean values. We added something that is not in the original syntax for array access. So in the original syntax, you can't access arrays in any way. We added additional filtering for time intervals because we found out that the general comparators are not very helpful for working with time spans, and so on. So we added Allen's interval algebra, where we add some new keywords or functions for time filtering, and we also added filtering, what we call filtering delete. The standard defines that you only can delete a single entity. We say if you can query it, you can delete it. So we support all the filters on delete queries. For example, deleting everything that is older, all observations that are older than 1 month. So filter by the phenomenon time. Greater now minus the duration of 1 month, for example. Okay. We added additional functionality for ID handling. So IDs, it's not exactly clear how IDs should look like in the standard. So we thought, okay, there might be multiple logical implementations, for example, long values or UUIDs or strings. And the ID generation method is quite clear in the standard. Basically, the only allowed one is server defined. So the IDs are always auto-generated. But in reality, we found out that there are quite a few use cases where you want to actually reuse existing IDs from other systems or from a backup maybe. And so we provide also these as a functionality and also some mixed functionality. If you don't provide an ID, then it's auto-generated. Okay. For the deployment of a Frost server, you have basically 2 options. You have the all-in-one option, and you have the separated HTTP and MQTT components. And each of these 2 ways or 2 options you can deploy as either a Docker or as a Tomcat, or you can deploy it via the Spring Boot application, which is by a third-party Kinota server. So these are basically the options you have for deployment. The all-in-one approach or deployment looks like this. So we have one database in the background, and you have one virtual machine, Java virtual machine, for example, Tomcat, and you have the 2 components running there, HTTP and MQTT, which are communicating, of course. If I create a new entity via HTTP, I must forward that information to MQTT to notify the subscribers. And then you can have a separated HTTP and MQTT. So each component can run runs in its own Java virtual machine, and you can have multiple instances of them. So that's better for horizontal scaling. You can add additional MQTT clients or services for better MQTT performance. And there you need, of course, some kind of message bus that can communicate between these services. And by default, the Frost server uses MQTT again as a message bus here. if you use this deployment. So you can have a Docker deployment, for example, with very few steps. Of course, first of all, you need to install Docker and Docker Compose. Those are, the tools you need. Then you can download the Docker Compose file. There are two actually in our GitHub repository, one for the all-in-one deployment and one for the separated deployment. And basically you then just have to run that file. For the all-in-one deployment, you can just call Docker Compose up. And for the other one, you have to provide the file path. And if you open your browser, you should have a running Frost server on your machine. So to play around, it's only like 3 steps. And additional to the Frost server, we have some more software, which we call the Frost Landscape. We have officially released ones that are on our Fraunhofer ISD GitHub account. So we have the server, we have a client library in Java. We have Frost Manager, which is like a basic GUI to manage the entity, so creating things and so on to actually browse your data and create new things. And we have Helm charts, which are like needed for deployment in Kubernetes server clusters. And then we have some experimental tools on the GitHub account of my colleague Hilke van der Saaf. For example, simple dashboard you can use to visualize your data. Processor, SensorThings processor to do data housekeeping, for example, so accumulate observations over 1 hour and then stuff like this. The SensorThings importer, where you can import data from CSV and I guess also other data formats. And some SensorThings copier, we can copy between different servers, which is also quite common use case, I noticed. Surprisingly, I didn't expect it to. Okay, so basically that is my presentation, and are there any more questions regarding Frost server?
I have a simple question. If I wanted to install on a Raspberry Pi, I would take the all-in-one install and compile it on the Raspberry Pi itself, or is there a ready-made Raspberry Pi image I could use?
There is, I think, not yet a ready-made image, but you can manually install the jar file or manually run the server. There's documentation on the GitHub wiki, not especially for Raspberry Pi, but it more or less works also for Raspberry Pi.
Yeah. Okay.
So you only have to make very slight adjustments. Yeah.
Is there a best practice available that shows how to do this in a high available 24-hour setting? This Frost setup.
So the question was if there is any documentation or best practice available how to set up Frost server for high availability or no. Short answer. Not yet.
You said there was time conservation.
Yeah.
How do you do it? Interrupt it, data to see what time it is, or is it the original time password?
I actually have to. So the question was how we do the type conservation, and I must be honest, it's been over a year since I've written that code, so I must have a look at it. I know we store like the original value as a string value in the database, but we also I think we have different types of columns in the database for different types of values. Where we actually, so we store the value multiple times once in the original format, like casted to its type, and one time as a string. Because as you've seen with the exponential values and the precision, yeah, I think that was the only way we could work out that it's actually giving you back the exact format that you've inserted. Yep.
What options are available to deal with secured transports, configuring the security, working the keys, whatever within the product?
Okay, the question was what kind of security is there available there for working with the Frost server. So first of all, the SensorThings API standard does not cover security at all. Frost server does provide an interface for authentication and two implementations, so basic authentication and the second one is with the framework which is called Keycloak that you can use. So yeah, and we kind of added our own rather simple security model on top. So because the standard itself does not define any security model, which comprises, I think, 3 roles, like administrator, read-only, and read-write access. Yeah, and you should also find some documentation on the GitHub page on that one. Okay. There's an online question. Okay, the online question is, can the SensorThings API and/or Frost server help me to find SensorThings sensors, sensor data, metadata on the web? Actually, no, I would say, because you have to know the server URL, and if you know a server URL of a Frost server, then of course you can discover what's provided by that server. But if you don't know anything, yeah, then probably the standard itself won't help you. Okay.
Just another question.
Okay. Is it possible to cascade SensorThings servers? I'm not 100% sure what you mean by that.
It's probably you have one front-end STA server and multiple back-end STA servers, and you sort of combine them. Maybe do that with WMS as well. WFS. That's not often used, but it can. I can imagine that it's.
In principle, I mean, from the standard definition, from the API definition, it's possible. From the Frost server implementation, maybe you can do something like this, at least for the. You will have to write some code and change some code, definitely. So there's no out-of-the-box support for this. But maybe you can make use of the custom ID feature here. Maybe that there is a project I know that uses multiple instances of the Frost server. So maybe there is an option for that.
So some elaboration to refer to data streams on other servers. I think your answer was clear.
Okay.
So, are there any further questions? Not I think we have plenty of time for questions in person this afternoon. So I think we'll move on to the presentation by Theo then. Thank you very much, Michael.
Thanks.
Full screen.
Even kijken.
Nou, ik zat er wel version bijna vol.
Yes. Okay.
Okay. Thanks, Jacob, for the presentation. I'll do the presentation in Nederlands. Want iedereen spreekt Nederlands, denk ik. Oké. Dan kan Jacob wat Nederlands leren. Ja, ik geef een presentatie. Ik ben trouwens Bert Timmer van Geonovum, van de Research Club. Ik ben hier samen met Tim Ebbe, is ook van Geonovum. En wij hebben gewerkt aan de Ghost implementatie van de SensorThings API.
Ja, dus dat pop-upje wegklikken. Anders blijft het misschien zo.
Dat is. Ja, nou een heleboel dingen hebben we net al gehoord over SensorThings en over de Ghost-implementatie. Wat ik in deze slides laat zien is erg vergelijkbaar, want het is dezelfde specificatie. Sommige dingetjes zijn net even anders, dus daar kunnen jullie op letten. Ja, ik had ook wat slides over de SensorThings API gemaakt, maar die ga ik allemaal even skippen, want dat hebben we allemaal net al gehoord. Model, vergelijking met SOS, dat was de oude specificatie, de Sensor Observation Service. Query samples, implementaties. Dan ben ik bij wat is Ghost? Nou ja, Ghost is gecertificeerd. Het staat trouwens voor, het is geïmplementeerd in de taal Golang. Dat is een taal van Google. En daarom heet het Go SensorThings. Gecertificeerd, we hebben er ook, net zoals Fraunhofer, 3 jaar ongeveer aan gewerkt. Dus 2016 en 2019. Het werkt op alle platformen, het is helemaal open source. We hebben onze eigen GitHub-organisatie. En daar kun je, dus dat is github.com/ghost. Daar kun je iets van 20 repositories vinden met allerlei code en tools. Het draait allemaal op Docker met Alpine images. Alpine zijn hele kleine images, dus je hoeft niet gigabytes aan data te downloaden. Ja, en in 2017 hebben we op Phosphor G in Boston een workshop gegeven. En als je de boel draaiend wil krijgen, dan raad ik aan om deze workshop te volgen. Hij was gepland voor 4 uurtjes. En dan leer je installeren en configureren en dan data koppelen en dan visualiseren. En dat wordt ook op Raspberry Pi. Ik ga in de volgende slides wat dieper in op deze dingen. Het is dus gecertificeerd bij de OGC. Dit is de architectuur. We gebruiken ook een relationele database open source, Postgres met Postgres. De blauwe blokje is de Ghost Server, dat is geïmplementeerd in Golang. Het heeft 2 endpoints, iets via HTTP en eentje via MQTT. En dan is er een dashboard, en dat dashboard draait op Nginx. En daar zou je ook nog eventueel beveiligingsregels kunnen stoppen. Als je dat wil. Ja, we hebben alles draaiend in Docker. In het begin hadden we nog installatiescripts en zo, maar dat werd zo een hassle. Dus we dachten we doen het alleen in Docker. We hebben 2 Docker Compose files. Eentje gewoon voor standaard dingen en eentje voor Raspberry Pi. Dus dat is een klein verschil. Met de grootste blokken. En eigenlijk de onderdelen die je in de architectuur zag, die kan je ook terugzien in de Docker images. Dus we hebben een database en een dashboard en een server. En dan gebruiken we nog wat standaard componenten. Node-RED staat een beetje los. Daarmee kan je flowcharts definiëren. Dat is een tool gemaakt door IBM. En we gebruiken Mosquito en dat is een server en die regelt alles met MQTT. Nou, net zoals Frost draait het op Kubernetes. Ik heb dus een blog geschreven over Ghost op Kubernetes. Het staat op ghostserver.xyz. En daar heb ik een test gedaan met Minikube. Dat is een eenvoudige Kubernetes cluster wat je kan installeren op je laptop. En dat werkte. En je kan het dus ook op een Raspberry Pi draaien. Daar heb ik ook een blog over geschreven. En daar gebruik ik een Raspberry Pi base image van Hyperiot. En daar zijn de Docker tools al op geïnstalleerd. Dus dat is handig. Ja, we doen heel veel benchmark testen. Want we willen dat de server snel is en niet omvalt. Dat is het belangrijkste. Eerst zien we wat testen met een tool die heet Apache Benchmark. En dan gaan we met 2000 users, 50 concurrenten, gaan we een bepaalde actie doen. En dan kijken we naar het aantal requests per second. Nou, zo proberen we een beetje te werken. Passen we code aan en dan hopen we dat deze getallen hoger zijn. Ja, waar gebruiken we Ghost nu voor? We werken samen met de Amsterdam Johan Cruijff Arena, moet ik zeggen. Wat we gedaan hebben, we hebben een soort dashboard gemaakt. Dat is gepresenteerd in de arena. We hebben allerlei data over Amsterdam Zuidoost verzameld. Over het milieu en over het verkeer. En allerlei datastreamen. Die hebben we allemaal verzameld in een dashboard. En Ghost draait dan op de achtergrond voor het opslaan van al die informatie. Nou, ik kan een live demo geven voor wie geïnteresseerd is. Moet je even bij mij langskomen. Nou, een andere is de PDOC Showcase. Dat is een Smart Emission project van Just. En PDOC. Dit is gestart in Nijmegen, maar is over het hele land uitgerold. En bevat nu 2700 datastreams. En dat draait in een Kubernetes cluster. Dat moet ik zeggen.
Vier cores en 8 groepen. Dus niet alleen voor Osten, dat blijft even. Ze hebben een heel ETL-proces bij en calculatie en database. Dat is de laatste. Ja, dat is de laatste. Nee, 5 nodes, dus 5 servers.
Ja, maar ook ja, maar VMS, VFS, SOS, eigenlijk allemaal met dezelfde data.
Ja, voor de online mensen, er is een vraag op hoeveel nodes draait dat Kubernetes cluster van PDOC? En dat zijn er 8. Ja, en dan draaien er allerlei tools ook nog op de achtergrond. Ja, voor die Getting Started raad ik aan om de Ghost Workshop te volgen. Die is in 2017 gegeven. Het gaat over het ophalen van verhuurfietsen. Van een bike station. En die in Ghost stoppen en dan visualiseren. Het begint met de Docker Compose Up en dan komen allerlei tools worden gebruikt. Nou, eentje is natuurlijk Docker. De meeste mensen gebruiken Docker Desktop voor Mac of Windows. Dat is een beetje de standaard tool. Maar je moet er een vrij nieuwe machine voor hebben. Een wat oudere optie is Docker voor Oracle VirtualBox. Die is wat lastiger aan de praat te krijgen, maar is te doen. En er is ook een site, die heet Play with Docker. Dan moet je inloggen en dan kan je voor 4 uur een Docker machine krijg je dan. En dan kan je leuk mee experimenteren. Nou, dit is het dashboard wat bij Ghost komt. Dit draait dus op Nginx, dus gewoon HTML en JavaScript. En dan krijg je een overzicht van alle things en datastreams en locations en observations. Dus dit is eigenlijk een soort beheertool. Nou, zo ziet de Node-RED eruit. Hier kan je helemaal wild gaan in het maken van een soort workflow.
Bij de microfoon blijven staan, heeft heel veel moeite dit te verstaan.
Voor de GIS-mensen het lijkt een beetje op FME, maar dan is het open source. We hebben ook een repository met Postman, dat is een welbekende tool, neem ik aan. Dus we hebben een JSON-file gemaakt met 79 SensorThings requests. En dat is handig, dan hoef je ze niet zelf samen te stellen, maar dan kan je gewoon klikken en dan uitvoeren. Een andere tool die in de workshop gebruikt wordt is MQTT-FX. En daarmee kan je publish subscribe op een MQTT-server doen. En dat is handig voor debuggen. Kijken hoe het werkt met de MQTT. Een andere tool die Tim gemaakt heeft is Ghost Connector. Dit is een Go-tool en die haalt data op van externe bronnen en pompt ze door naar Ghost of naar een SensorThings server. En configuratie gaat via een JSON-file. Dus als je je eigen weerstation hebt en je wil data van je weerstation naar Ghost krijgen, dan zou je deze tool kunnen gebruiken. Oké, nou dat is wat wij gemaakt hebben. Momenteel zijn we bezig om te kijken of we ook andere databases erin kunnen stoppen. Want we merken dat als je heel veel observaties doet, dan wordt de observations tabel heel groot en dan kan die traag worden. Eén optie waar we naar kijken is timescale db. Die hakt je observations tabel in stukken op basis van tijd. En dan beloven ze dat je nog steeds dezelfde query kan doen. Dus daar zijn we naar aan het kijken. Andere database waar we naar kijken is ClickHouse. Dat is een column store database. En die is waanzinnig snel. Ja, belooft heel veel, maar we moeten kijken hoe we dat kunnen combineren met SensorThings API. Ja, de tasking profile willen we toevoegen. We willen dingen doen met machine learning en AI voor het doen van voorspellingen op basis van observaties uit het verleden. En we zijn bezig met een nieuwe dashboard gemaakt met Polymer en Web Components. Dat is de moderne JavaScript. En dat was mijn presentatie. Zijn er vragen? Daar niet.
Waarom wordt ervoor gekozen om alle observaties in het platform te houden? Waarom wordt dat niet overgedragen naar een business intelligence of machine learning, big data omgeving? Ook Frost had dezelfde insteek. Wat is de waarde om dat in die constructie te maken?
Ja, de vraag is, waarom slaan jullie de observations allemaal in de database op? En waarom gebruik je niet een externe dataopslagmechanisme daarvoor? En de reden is in ons geval, en ik denk ook in het geval van Frost, was dat dat de makkelijkste manier van implementeren was. Om snel iets running te krijgen. Want je hebt ook al alle metadata zit al in de tabel en soms wil je gecombineerde queries doen. En dus dan is het makkelijk als alles in één database zit. We zouden het is allemaal open source en we zouden het kunnen aanpassen.
Het heeft een soort, zeg maar, een dubbele betekenis. Het is ofwel het ontvangstpunt van alle sensordata en voor je directe dagdagelijkse werkzaamheden een soort vraagpunt. Maar voor je trendanalyses en voor je lange termijn besonderingen en je machine learning zou het niet logisch zijn om, zeg maar, minder snel de sensordata kwijt te kunnen omdat iemand een query draait. Dat hoor ik in deze. Misschien zat er, ik was benieuwd of er een best practice achter zat om dat toch te doen, want ergens anders hebben we het niet, zijn we er tegenaan gelopen. Dus dat is duidelijk.
Ja, maar bedankt voor de suggestie.
Ik kan nog wel iets over zeggen dat we in een POK doen bijvoorbeeld, dat in het ETL-proces van binnenkomende sensordata gaat die data naar meerdere zeg maar targets. Dus er gaat ook bijvoorbeeld exact dezelfde data, komt in influx erbij. En dan kan je weer ander soort queries doen. SensorThings API kan je bijvoorbeeld geen aggregaties doen, dat soort dingen. Zelfs naar postgres. Dus dat is de manier waarop we zeg maar ook meerdere soorten van toegang kunnen verlenen. En Nou, die data is dan eigenlijk identiek wat er dan in de host server zit. In Postgres doen we ook met VMS en WFS. Andere wereldse doen. En zelfs in FluxDB.
Misschien is het interessant om te kijken naar de documentatie van...
natuurlijk, maar als je dat zeg maar in de ETL-proces hebt geëmbed, dan is het eigenlijk alleen maar tot meer storage.
Jij bedoelt denk ik meer het aggregeren van oude data, toch? Dat je niet meer precies weet wat 5 jaar of 50 gekomen of 1 minuut data is, en dan weer de trend vast.
Nou, het leek me de meeste best practices om alle observaties in hetzelfde systeem te stoppen en je analyses te doen als waar je je sensorgegevens in ontvangst neemt. Het leek een beetje zeg maar een betaalterminal of een betaalsysteem en dan stop ik al mijn afschriften van de afgelopen 12 jaar stop ik in diezelfde database, zodat ik prachtig met die API's dingen kan doen, maar het leek me zo onnatuurlijk. En ik vroeg me af of er juist in het sensorwereld, en betalen is een compleet ander, in de sensorwereld juist wel een belangrijke best practice was. Hoorden wij dat het enerzijds een gemakselement in zit en anderzijds dat er eigenlijk ook wel bewegingen zijn om die informatie gewoon te dupliceren naar een andere rol.
Ja, want het is ook uiteindelijk volgens mij een soort ontsluitingsmechanisme voor bepaalde clients, bijvoorbeeld met name viewers en zo. Maar als je echt analyse wil doen, dan heb je eigenlijk vaak weer andere vormen van opslag en zo.
We zien wel dat alleen met het installeren van een SensorThings server ben je er niet. Want je wil ook nog allerlei andere processen doen. Je wil bijvoorbeeld controleren, zijn de waarnemingen die opgestuurd worden, zijn die wel valid? Hoe zit het met dubbele waarden die worden opgestuurd? Dus zo zie je dat er een hele set aan tools gebruikt wordt. En het is wel goed om naar het Smart Emission, want jullie hebben zo'n mooi architectuurplaatje gemaakt met allerlei tools. En het is wel leuk om naar te kijken in ieder geval.
Goed, je kan natuurlijk ook die SensorThings API voor je eigen analyse natuurlijk gebruiken. Omdat je op allerlei mogelijke manieren die data eruit kan filteren.
Maar is die daarvoor bedoeld? Dat is op zich een interessante vraag wat precies de use case van zo'n API is. Want je kan inderdaad complexe queries doen, maar wil je dat überhaupt doen op de SensorThings API? Wil je de data binnenhalen en dan vervolgens die bak data die dan zo gecreëerd je eigen queries zijn op zo'n BI-achtergrond?
Maar dat kan ook nog steeds natuurlijk.
Ja, dat kan allebei.
Ja, dan kan je van alle OGC-standaarden natuurlijk afvragen.
Ja, maar
bij WFS ook. En dan heb je weer zeg maar vector geodata. En daar kan je natuurlijk ook heel interessante dingen mee doen.
Maar ik vraag me dus, want jij zegt een viewer, dat zou dan een use case zijn, maar ik neem niet aan dat dat een use case is voor de SensorThings.
Nou ja, ik zie het vooral als middel om, bijvoorbeeld in die sensorwereld, dat is ongelooflijk gesegmenteerd. Er zijn allerlei projecten en uiteindelijk willen we een landelijk beeld van bijvoorbeeld stikstof of dioxide. En om al die initiatieven met elkaar te kunnen verbinden en bijvoorbeeld centraal te ontsluiten, zou het heel handig zijn als al die initiatieven ook allemaal als SensorThings API met misschien nog een landelijk profiel, hoe we zeg maar met al die opties nog omgaan die erin zitten. En dan, dat is denk ik een use case om...
Ik wil graag deze discussie nu even stoppen. Ja. En die kunnen we zo meteen aan het einde van de webinar wel weer voortzetten. Dan kunnen we ook daarna gewoon gelijk gaan terugkoppelen van wat zijn onze doelen en wat willen we gaan doen vandaag. Maar ik denk dat we nu even terug moeten naar zijn er nog echt basisvragen over hoe werkt de Ghost implementatie. Misschien wat ik ook nog wel interessant vond, de slide waar je aan voorbij ging, was de verschillen tussen SOS en Ghost. Ik weet dat in ieder geval één iemand hier in de zaal zit die SOS al heeft geïmplementeerd, maar volgens mij ook SensorThings. Dus is daar behoefte aan om daar nog naar te kijken? Nee, die is niet groot, die behoefte.
Naar wie kijk je nu?
RIVM volgens mij dan.
Ja, we hebben wel SOS, maar dat weet ik ook heel erg van.
Oké.
Maar ik heb geen vraag over.
Nee, helder.
Ja, we hebben er bij Geonovum allebei gedaan.
Ja.
Zoals SOS en PDK.
Is SOS al een zeg maar een meer historische standaard en is dit een manier om je nu op in te werken of heeft SOS voordelen ten opzichte van deze systematiek, waardoor het wel de moeite waard is om als organisatie die nu begint daar energie in te stoppen?
Ja, die SOS-standaard die is al wat ouder, dus die is wat meer volwassen natuurlijk. En heeft veel meer best practices. En, ik verwacht zelf wel dat SensorThings het steeds meer gaat overnemen. Dat die gewoon wat bruikbaarder is in praktijk.
En de leveranciers die sensoren maken die out of the box SensorThings goedgekeurd, gecertificeerd, compliant ondersteunend zijn. Dus kan ik naar Amazon gaan en daar 50 sensoren kopen waarin staat SensorThings Inside of zo.
Ik had nog één sheet met implementaties van de SensorThings API. Er zijn nu 2 open source, Frost en Ghost. Eentje is nog een closed source van SensorUp. Dat is een Canadees bedrijf. Dan is er nog 1 implementatie van Mozilla, geloof ik. Maar that's it op het moment. Dus het zou mooi zijn als er ook een sensorfabrikant zou komen die aansluit op de SensorThings API, maar daar heb ik nog niks van gezien.
Ja, in de praktijk doe je dat. Zou je bijvoorbeeld wel, zeg maar, MQTT vanaf die sensoren doen met een Ghost, ja, zeg maar, conventie, maar direct op de sensor komen. Nou, misschien is het wel zin om.
En 52 North. Ja, Edwin heeft een toevoeging. 52 North is een Duits bedrijf. En die hebben een SOS-implementatie. En zij hebben daarbovenop een laagje gemaakt. En die converteert, of die naar buiten toe exposeert hij zichzelf als SensorThings API. Maar intern had hij dan SOS. Dus dat was een goede toevoeging van Edwin. Ja.
Ik stel voor dat we doorgaan naar de presentatie van Philip. Zodat we min of meer binnen de tijd de webinar kunnen gaan afronden. Ja.
Wel, gewoon de boel opzet. In het Nederlands of in het Engels? Maakt mij niet veel uit, maar wat willen jullie? Nederlands, English or Dutch?
Yeah, or if there's slides or English, then.
No, well, there's a lot of pictures there. But, okay, I'll do it in English then. I hope it doesn't hurt your ears because my English pronunciation is not as good as my Dutch one. But the girls at home say that the same as well as for my Dutch. Okay. I'm a bit of an outlier here. I'm a hydrogeologist and I'm just involved in generating data. Well, then the data are handed to some IT thing and then I'm also involved in analyzing them. And that's what I'll talk about a little bit. Frank asked me to supply some groundwater data, so I'm going to tell you what those data are all about and what we can see in them a little bit. Here's the classical method on the right side of measuring data. You see a groundwater monitoring well. There's a piezometer in it. And somebody's having a long wire with sort of scales and he's measuring the depth of the groundwater table. So that's what we hydrogeologists are interested in. Hoe gaat het ding door?
Pijltjes.
Pijltjes, we kijken. Let's see. Well, this is all in Dutch, but I'll translate it for you. It's we are dealing with time series, long time series. In Waternet we have groundwater data from 1852. That they're still digitized, and the oldest digitized ones we have in digital form are from about the start of the 20th century. And that's because groundwater is flowing very, very slowly. It takes a lot of time for groundwater to move. We have some data for you, but I have to prepare them later on during this webinar. It's about Amsterdam water supply tunes. It's a drinking water supply area, and it started all around 1853 for the first time.
we call it, the specs of those data is we have several sorts of groundwater flow systems there. I'm standing in your way. Can you see the pictures? We have what we call very fast systems for hydrogeologists, but it's still just hours to days. That's about tides in the North Sea and very quick adaptations of the groundwater recovery system. There's a sort of slower system. It's driven by precipitation, which goes down. The influence of it is in the order of days or weeks, and that's because of the memory of the groundwater system. It's in that order. But there are also even slower systems there, seasonal systems and climate systems. And they have a very, very slow system in the order of centuries, and that's relating to the distribution of saline and fresh groundwater in the subsurface. That system has a memory of about 3 centuries. Then I have some other data for you. It's from the south of the province of Utrecht, where we have a groundwater abstraction thing. And it's all very fast systems for our hydrologists in the order of days again, because everywhere the surface water levels are controlled. That's not the case in the Amsterdam water supply tunes. But there's also tidal influence from the River Lek. You wouldn't believe it, but I'll show you a picture later on. And of course, we have the influence of very quick adaptations of the groundwater abstractions there. Not only our groundwater abstractions, but our colleagues from other water supplies are nearby. So, still legible for you? Oh, this is just a.
It will drive.
Yeah, it should be. I hope it's good. So, what can we see in those time series? Well, we see the fluctuations we expect. Tidal things and some parts of the water supply because we drive it ourselves. You have the harder to predict things like precipitation or other things, maybe also air pressure, which doesn't sing, and also parts of the water supply we can't predict. And of course, a lot of errors. And that's I'm going to tell you a little bit about, because that's what's always bothering us. We have sensor data, maybe not online, but we have sensor data. But sensors is not the same as a groundwater. There's a lot of translation in between, and that gives rise to a lot of misinterpretation and errors. You have to be very careful. And that's something. Okay. First of all, what does a groundwater monitoring well look like? Well, on the left-hand side, you see a picture of some sort of tube. And if you open it up, you see a lot of things inside, and if you don't mind, I will walk to to just point it out to you. Or can I do it here? Is it a pointer? No. Don't touch it. So I'm sorry for the people. This is a golden model. If you look at it, you see all kinds of ipsometers with long tubes. We go to 120 meters here. Not all of them. One is a 10 meter, another one is 50 meter, another one 30, another one 90. And they all measure different groundwater heads. And heads is a sort of measure for groundwater pressure plus a sort of position parameter. And that's important for us because groundwater head differences, that's what drives groundwater flow. Actually, here you see a more interesting thing for you. That's a hook, and on that hook there is hanging a sort of sensor. I'll show you it later, which measures the groundwater pressure, or actually measures pressure. The pressure has to be calculated into groundwater heads later on. And here on the left side is a more complicated well. It also has all kinds of mini filters, and it also has a sort of cable for measuring resistivity in the subsurface. What that also well look like. How is it well made? It's also it's a bit of a complicated one here. This is what we call a filter, a piezometer filter. That's the thing which is down in the subsurface, 1 meter or 2 meters length, and the rest of it is like this. It's just impermeable, so you actually measure the groundwater, or you somewhat sample groundwater at large depths.
We at Waternet also use mini filters, very small filters, mainly used for taking groundwater samples at depths at a very precise level. And well, this is the way this mesh is what is installed when trying to make a big well. It takes several weeks. This is installation. And well, usually the biggest thing to make sure that all those little tubes aren't entangled in each other. It's a lot of work. And at the end, well, you have this. You've got piezometers, a few smaller pipes for the mini filters, and the orange thing is the electric cable. And then you put a sort of cover around it, and that's it. So, maybe you're a bit flabbergasted because I'm completely from another universe for you, but it's important to tell you, I think it's important to tell you what data is all about. Now, this is what the sensors look like. I shamelessly copied it from the website of a supplier from us. This is a pressure transducer. It's hanging on a piece of wire at well, certain depths. If you unscrew this, you see a sort of membrane, and the membrane is sensitive for pressures, and inside is all kinds of electronics. It measures the temperature, it measures pressure, and the temperature is required because the membrane distortion is also dependent on temperature. So we measure actually pressures, and the temperature we get for free. It's also very handy for our hydrologists. Well, then you come by with a computer, you put it in a sort of unit, and then you can download the data. That's how it works. And of course, it's also possible to do it online with a special cable up to the top, and then with GSM and GPRS or so, whatever. And this picture is nice weather, but it's usually raining when you trying to feed them out.
Weet je zeker dat hij op de juiste diepte blijft hangen?
Yeah, well, that's a good question. The question is, how are we sure that this pressure transducer is kept on the same level? Well, that's one of the problems. We usually attach them to cables which don't stretch, but we have our doubts about it. It's a special sort of rope, sort of Kevlar rope, which shouldn't stretch unless you have very large weights on it. But because the thing is in the water, it's also its own how do you call it? It's the Archimedes law. It's not as heavy in water as it is in the air, so it doesn't hang as much to the cable itself. But we have problems with it sometimes. If I go back, I'll show you this little hook here. Sometimes in groundwater samples or people just take the thing out for some sort of maintenance, they sometimes forget to properly put the hook back. It's hanging outside of the piezometer for 10 centimeters. But we usually detect it in the time series. Satisfied? Okay, let me see. Yeah, okay, well, here's an example of a time series. Groundwater time series in the bottom applied units, and what you can see here is actually the influence of North Sea tides on the groundwater, and also precipitation, because those are the only influences we hydrologists can imagine that we will be working on groundwater there. So you see very fast fluctuations twice a day. It's the tidal influence of the moon of the It's dominating here. It's about 25 hours for 2 cycles. And if you enlarge it a little bit, well, we can also filter out the tidal frequencies, and then you get the red line there, which is supposed to be more representative for what happens because of precipitation. So that's nice to do. Here a little bit about errors in time series, and one of those things, of course, well, the first one was how are you sure that the sensor is at the same depth? So that's operational error, but we also have sensor errors. Here you get one of drift because of well, the sensor itself has a sort of drift. You see these little points here. These are actually hand measurements. Every 3 months or so, somebody comes along and
get the data from the logger, puts it back, and also measures the groundwater head with a manual gauge. And then you see in time that the difference between what the measure says, it measures after calculation, and the hand measurements is slowly increasing. So it used to be just 1 centimeter or so. It slowly increases. You can see at the end it's almost 10 centimeters, so that's sort of drift. But this, well, we don't care in this case too much because the data still appear to our hydrologists as genuine. But we have cases where we can, well, it's sort of gut feeling where you know that it's very unreliable, and usually you see that there are different fluctuations in the time series. But it's very hard to assess. So this is just drift of the sensor itself, of the membrane. But we also have drift in the internal clock of the data loggers. And that's very hard to detect. And actually, we could only do it in the web body applied use by computing the phase lags with the tides. And then you get interesting things. In 2010, I made up a new monitoring scheme, and then we decided to, first of all, what we never did, write down the time that measurements were made. There's a 15-minute accuracy that was enough for groundwater. Before the time, people just noted the day. And we also found out that all the time without sensors we have been neglecting summer and daylight saving times. So you can see it here. It's just a 1 hour time difference all the time because nobody was taking care of it. We only realized it in about 2010. And then we also changed the data logger, and now what you can see is that there is so drift in the time scale of the clock of the data logger. You can also see it's a linear drift. That's not guaranteed, but it's maybe 1 out of 10 of our data loggers has this time drift. And remarkably, it's almost always in the same order. So we are looking if we can at the serial numbers of our data loggers, if it's maybe some sort of batch. I don't know. But also we try to reset the clocks. We restart the data loggers every year annually, but sometimes it's missed. So you can see that here. This was a 3-year interval we forgot, and the next period is done every year. Okay, that's about this, and then this is the last of my slides. It's just to show you that we also have tides in the Lek River in South Utrecht. It's about amplitude of 1.4 meters. It's coming all the way from the mouth near Rotterdam of the Lek. It's coming all the way, maybe a bit of westwards. It's also dependent on the discharge of the Lek. If the discharge is very high, that totally dominates the water levels. And we also see that in the groundwater for a long way. Well, this was about my presentation. This is all I have for the moment. I will have to generate a few data for you, but I can do it in this discussion with you, what you want to see of it, and what file formats. It's actually a very simple format.
Yeah, so you sent me some examples, right? So
yeah, there are some more, and well, you can play around with it.
I think you have different sensors. One that produces pressure, salinity, and temperature.
Yeah, we would have to dig it up. It's salinity, actually electrical conductivity.
Yeah.
And well.
And there was another example that you have temperature and groundwater level directly.
It's always temperature and groundwater levels. Yeah. Or actually, pressure and temperature. Those two.
It's always pressure and temperature.
Yeah. Any questions? Yeah, this is completely different field for you, so that's okay.
Are the waternet data in general open for public? Or?
Yeah, well, they are collected with public money, public funded, so they should be open. But we are slowly turning into. Well, the raw data is a bit can also be open. We are not against supplying it. If you ask us, you can get them. It's easy, but it's a lot of work to get it organized. And now Frank and I know each other from the BRO, de basisregistratie ondergrond. In that course, we will probably open up also historical data, but there is a little bit of thinking about, because it's very well. You need to be a hydrologist to properly assess and analyze those data. There are a lot of gotchas if you see a groundwater head time series of what actually happens there. So it's a bit, we are a bit reluctant to open them up without any context. But it's going to happen, so we're going to do it. But, yeah.
Do you analyze the raw data, or are we looking at some kind
Both of them, yeah. We for the hydrological thing is we do the process data. It's recalculated into head time series. But if you don't trust it, we go to the raw data.
How do you recalculate the data?
Well, the pressure is the sensor. They measure absolute pressure. So we first have to subtract the atmospheric pressure, the ambient pressure from it, and then we get the groundwater head. But it's not an absolute groundwater level, but a relative. So we have to relate it to absolute levels and HP levels, if you want. Well, there are a lot of error sources in there already, and then it turns out that depending on the geohydrological situation, we can also have atmospheric influences on the groundwater itself. It's like sometimes it's between clay layers. It's like a box. If you put pressure on the box, it gets squeezed out, the water. It also happens under your feet. So there's a lot of things going on there. And,
we don't have a pressure sensor per well to measure the ambient pressure, because
we usually take the data from the Dutch Meteorological Organization. We used to have them ourselves, but they're prone to the same problems as the water level sensors. The battery runs out, or they get drift, or they are well. It's better to rely on the Meteorological Institute.
Are they co-located enough?
No. And we have to take care that every 8 meter, that's another hectopascal. So you also have to take into account the absolute height. There's a lot of, it's hard to properly recalculate them into groundwater heads. It can be done, but you have to be aware of all the steps in between. And every step has loads of errors. Potential errors. So let's see if there are any questions here.
I haven't seen any up here yet.
Not for me. No.
For the purposes of the hackathon, we will be supplying some example data with Philip, so it will be public. I'll put a disclaimer there that it's just example data for this hackathon, but everyone here can use it, and everyone online can use it as well.
Yeah. Okay, any other questions? No more? Okay, thank you.
Okay. So, I will try to wrap up the online webinar part. So, as I just said, I'll be making available some of Philip's data online. Also, I'll be working to have the recording of the session online as soon as possible as well, together with the presentations. One question I have for the online participants, would you be interested in an online communication channel, for instance, a Slack for communicating while the hackathon is taking place? If so, please let me know, then I'll start a Slack channel where we can all participate, both people that are here and people that are online. And I'll try to get the information on the Geonovum website at the location of our announcement of the webinar. Yeah, so there's a need for Slack, so I'll get our a Slack channel up and running this afternoon. Are there any additional questions from the people online? And maybe specifically, do you want to do some hacking, and do you need help from anyone that's in this room? And if not, I'll be closing the webinar, and then later on you can ask questions using Slack. In Nederlands, we kunnen via Slack dan later met elkaar communiceren. Dat zullen we via de Geonovum website laten weten. We kunnen het ook rondsturen aan iedereen die zich heeft opgegeven. Maar ik vermoed dat niet iedereen die online is zich ook heeft opgegeven. Dus dan bij deze, iedereen die online is, bedankt voor jullie aanwezigheid. En dan ga ik de opname even opzetten.